Welcome back to the Envirotech Online podcast, your go-to source for insight into the fast-evolving world of environmental monitoring. As always, I'm Jed Thomas, editor of Envirotech Online.
And hello, I'm Alan Booth, Senior Editor at ILM Media. Jed, in today's episode, we're going to take a big picture look at the last 2 decades of PFAS monitoring, covering what we've learned and asking what needs to change.
That's right. A new study published in Water and Ecology uses bibliometric analysis, that's a structured review of published research, to trace the trajectory of PFAS monitoring between 2003 and 2023. It examines over 1,200 publications to draw out trends and future trajectories for researchers and monitoring professionals to explore.
And it tells a pretty compelling story, right? A story of how monitoring has responded to regulation and struggled to keep pace with all the new chemical compositions involved in the ever-changing profile of PFAS contamination.
Well, let's start with the obvious shifts. 20 years ago, PFAS monitoring was a niche concern, mainly restricted to academic labs and a few water utilities with specialist capabilities. But as of today, PFAS monitoring is a global priority that is part of drinking water safety frameworks, product regulation, industrial permitting, and public health planning. According to the paper, the tipping point came after 2017, when the US EPA issued health advisories for PFOA, that's perfluorooctanoic acid, and PFOS, perfluorooctane sulfonic acid, two of the most well-known legacy PFAS. That led to a surge in research and further regulation, particularly in the European Union and East Asia.
The message for the researchers here is clear. Monitoring expands only when regulation forces it. The curve, which shows publication of scientific papers, is flat until the mid-2000s. It grows slowly through the early 2010s, but then spikes dramatically post-2017.
And that has implications for the future of PFAS monitoring. Monitoring doesn't scale with scientific curiosity. It scales when it has to. When standards tighten, networks grow. When standards stall, research plateaus. It's a reminder that science often follows rather than leads policy. The second big finding is about what we're missing. After 20 years, the majority of PFAS monitoring still focuses on legacy compounds, primarily PFOA and PFOS. These are important, but they're just the tip of the iceberg. Short-chain PFAS and novel fluorinated compounds are widely used in textiles, coatings, food packagings, and industrial processes, but we don't look for them nearly as often as these legacy long chains. Why is that?
Because they're harder to catch. They're more mobile and don't bind to soils or sediments in the same way. That means they show up in unexpected places and often in concentrations which are below current and historic detection thresholds.
So standard LC-MS methods can capture them in principle, but these methods are expensive and labour intensive. That can limit the scope of sampling campaigns.
So the result is a patchy global data set that may not catch contamination early enough to intervene. And that's a big concern if you're trying to protect drinking water at the system level.
And that leads us to a third insight from the paper. Lab analytics alone are not enough.
For most of the last 2 decades, PFAS monitoring has depended on centralised laboratories running high-precision LC-MS squared. That makes sense when the field is in its infancy.
But today, with rising demand for real-time data and broader spatial coverage, we're seeing the limits of that model. Centralised labs can't give us the temporal resolution or the network density that we need.
The study points to field deployable sensors as a partial turning point. These offer faster detection at a lower cost per data point and a better level of integration into distributed sampling frameworks.
But, and this is key, deployment is still inconsistent. Some utilities and researchers are using these tools, others aren't. And the data they produce often isn't standardized or interoperable.
That's a problem for shared infrastructure and trend analysis. 2 decades of evidence suggest that unless sensor networks feed into unified data systems, we'll continue to see fragmented monitoring landscapes. So what does the next decade need to look like?
The paper makes a few recommendations. First, we need monitoring frameworks that target all classes of PFAS, not just the ones we already regulate. That means updating analytical libraries and prioritizing chemicals with high mobility and persistence. Second, lab-based methods need to be supplemented, not replaced, by field sensors. That's the only way to get the temporal and spatial resolution that we need. Third, the data infrastructure has to catch up. Monitoring data should flow into unified platforms that support decision-making, policy development, and public communication.
20 years of PFAS monitoring may have brought us a long way, but it's only revealed where our systems need developing.
And for our listeners working on PFAS monitoring, now's the time to align your practices with a new model of exploratory monitoring, harnessing different technologies to get there.
If you want to stay ahead of that curve and explore the latest in PFAS monitoring instrumentation, make sure you're subscribed to Envirotech Online.
We've got over 100 hours of expert video content on the site, including sessions on PFAS detection, field sensors, regulatory trends, and analytical strategies. Just head to www.envirotech-online.com to sign up for free today.
That's it from us. Thanks for tuning in.
Until next time.